Important point. You do a logistic regression, kind of here's some output that you'll often see whatever software you do. Something to just, especially if you did not code your variable 0, 1, at least with SPSS, but I think probably all the software, look to see how it's coding your variables. It may come out and tell you here the original value and the internal value. Sometimes I've seen people where people would do like 1 and 2 for their outcome, and then they plug it in. Logistic regression won't work with a 1 and a 2. It's got to be a 0, 1. So it will internally make one of them a 1 and one of them a 0. And there was some version of SPSS years ago that if you coded it 1 and 2, it would make the 1 the 1 and 2 the 0. And people instinctively would think, well, 1 and 2 should, 1's going to be the 0, 2's going to be the 1. But it basically flipped which one was which internally, and all of a sudden you're reading your results are opposite what you think. So kind of, I haven't tried that for a while, but anyway, so kind of pay attention to, which you want to know. Well, your regression, remember, your logistic regression model is predicting 1s. It's predicting your odds of being whatever a 1 is. Make sure you know what that is. And as we've said numerous times in the past, if your results seem odd, double check it because it's probably wrong. I mean, especially if you're interpreting things the backwards, the opposite of what you would think it would be, that could very well be what it is. You've got 0 and 1 flipped. There's a really cool number here, and you'll see this. The -2 log likelihood is used a lot in logistic regression. It's actually used a lot in other statistical kind of, as we move into more advanced statistical approaches, you'll see the -2 log likelihood used a lot. And what it is you can think of it as it's an indicator of the lack of fit of a model with the data. So I'm proposing a model, and does this model kind of fit what we see with the data? We've kind of talked about this a little abstractly before, but here's a kind of one indicator, and if you go on to structural equation modeling, we're going to revisit this in other ways that really leverage how this works. That on its own, it's an abstract number. Is 81.5 big? God only knows. I mean, it's abstract on its own, but as we'll see in a minute, it can be helpful to understand how well a model fits. It's not particularly meaningful on its own. You might ask, why -2 log likelihood? The negative is just to make it a positive. You multiply it. You make it well. You think log because we're doing we've been dealing with logs. So you take the log. The negative makes it, otherwise they're negative values, so you multiply it by a negative to make them positive values, and the 2 makes it a chi-square distribution. But you don't need to remember anything of what I've just said. But it's kind of cool that the 2 is what makes it follow a chi-square distribution. But I'm just entertaining myself with that conversation, so I won't bore you. How does it work? What does that negative, to give you a sense of when I say it's an indicator of how well the model fits. Kind of one way that I think may help to see that is, let's actually go through the calculation once and only once for a -2 log likelihood. And keep in mind, in this case, we have a model with no predictors. Oops, I've started right now. In this model, it doesn't say it here. This is a model beginning block 0. SPS says that it's just a way of saying this is a model. Remember we have model with multiple regression. We do model 1, model 2, model 3. Model 0 is just there's nothing in the model because it wants to give you numbers like this. like this negative 2 log likelihood. So with nothing in the model, we're back to Sergeant Schultz. We know nothing, no predictors. If I had 25 if 25 out of 60 youth dropped out, what's the proportion of kids? What's the probability of a kid dropping out? Well, it's 25 over 60, or 0.41667. 35 out of 60 kids did not drop out. So what's the probability? 35 over 60 is 0.5833. The likelihood that I would exactly predict every single of those 60 kids. So every kid I've got to know, you dropped out, you didn't, you did, you didn't, you did, you didn't. What's the likelihood that I'd be able to exactly predict every kid? Well, I've got to get the first kid right, and I got to get the second kid right, and I got to get the third kid right. So think back to 573 probability, the multiplication rule. It's 25 of those times, probabilities, times each other, times 35 of those probabilities. So it's 0.41667 to the power of 25 times 0.583 to the power of 35. The probability of the likelihood of guessing everybody correct, completely knowing absolutely nothing, just by chance, is 2 to the negative 18. So it's a very, very small number. Okay? As you can see, it's a really small number. So taking the log, I mean, outside of we're doing the logs, helps to make it a bigger number. So the log of 2 to the negative, the log of that 0.000002, more zeros, is negative 40.751596. Multiply that by negative 2 log likelihood is 81.5. That's where the negative 2 log likelihood comes from. It's the negative 2, it's negative 2 times the log likelihood that we know what we're predicting, that we're predicting correctly. And this is based on we know nothing. Now, you can think of, if I know that your parents have a PhD, your parents don't, your parents didn't graduate middle school, your parents are, lawyers, I can do better than that. I can do better than that likelihood of guessing people are correct with more information. And that likelihood's going to get bigger because it'll be easier to guess correctly with other information. And that's going to get bigger, so that's going to get smaller. So my negative 2 log likelihood is going to get smaller and smaller as I'm getting more information and able to make better predictions based on the model. So again, it's kind of it seems like, and it is an abstract number, but it's telling us. It's a way of telling us how good our model is at being able to make predictions. And right now, it's based on, this is our ground zero. When we're starting, if I know nothing, this just gives me a baseline number to work with when I start to add variables. How well does this improve as I add more variables? Cool. So let's add parent education. So like we're just saying, notice now the negative 2 log likelihood is 64.227. We won't go through and calculate that, but you can see it's gone, as we said, it's gone down because we're able to make better predictions. It went down how much? It went down 17.276. The drop in that, how much our model has improved, is equal to 17.276. That follows a chi-square distribution. See, this is why I was rambling on earlier. That's why you like it follows to make it follow the chi-square. So it follows a chi-square distribution with 1 degree of freedom. The p-value is less than 0.0001. So this just tells us, this is one test for our new model after we've added You can think of this as, it's kind of like the change in R-square test in multiple regression. It's testing a new model after we've added some variables. How many variables? That's the degrees of freedom will tell us how many variables we added. In this case, we just added one variable. Here's our test. Instead of a f-test, it's a chi-square test with 1 degree of freedom. Here's our p-value. It did significantly improve our model. And if you, again, this is just how much our old negative 2 log likelihood went down by 17 to take us to this level. You can't think of these as variances. But in a way, it's kind of showing how we're accounting for that negative 2 log likelihood, that information that we were starting with. Okay? Notice it doesn't tell us the regression coefficients anywhere here yet. We're just looking at the, and there's all sorts of stuff here. It's doing iterations, it's doing maximum likelihood. Yeah, we won't worry about that. We just talked about this. It's the degrees of freedom equal to the number of variables we've added. Here's our regression model. Okay, just like with multiple regression, though it's a little twist to it, because like we talked about, we need to remember our outcome isn't y. This is the regression model for predicting the log odds. Here's our regression coefficient for the parent schooling effect. The constant, that's our intercept. So here's B1, here's B0. We can write them right here. So here's the generic logistic regression equation. The logit equals the log odds equals B0 plus B1 times X. We just plug them in. B0 is 4.6. B1 is negative 0.4411 times parent schooling. So there's our logistic regression equation. I'm kind of getting ahead of myself, right? There's that coefficient. We can calculate, right? The regression coefficient for parent schooling is negative 0.4411. I can calculate the odds ratio for that, because remember, that's predicting the log odds. You don't really want to waste time interpreting the regression coefficient in logistic regression. You might, if you want to make a graph of the probabilities, it's handy. But what you really want to do is turn that regression coefficient into a odds ratio. The output software will do that for you if you do this in just about any statistical software. So here we can see it already gave us, well, I asked for it to give me EXPB. Remember, that's another way of saying the odds ratio. EXPB is e to the b, which is the odds ratio. So here's my odds ratio for parent schooling. It has confidence intervals even, that's nice. So e to the b, or e to the, and you could calculate it by hand. If I didn't give you this, you could just calculate e to the power of negative 0.4411 gives me 0.6433. That's my odds ratio. So that indicates for every year increase in parent schooling, the odds of dropping out are 0.64 what they were the previous year. So they're going down by about, well, 1 minus 0.64, they're going down by about 36%, right about a third. So whatever the odds were, it's gone down to 0.64. Then in another year of schooling, it goes down by another factor of 0.64. And down by another factor of 0.64, and another, with each year. Alternatively, you can kind of flip that around, just like we said, do the inverse of 1 over 0.6433, gives me 1.55, and that says for every year less of school, the odds of dropping out go up 55%. So it's whatever the odds were, now it's times 1.55, another year less of school, times 0.155, 1.55 times 1.55, right? It just depends which way you're going. Pretty cool. There is the Wald test. That says, notice, you look at it there and you think, well, it kind of looks like the t-test, doesn't it? And it is kind of functionally like a t-test in that sense. It's testing that specific regression coefficient. Some have noted problems with the Wald test. So in general, we prefer doing the difference in the -2, at least I prefer doing the difference in the -2 log likelihood instead of the Wald test. Notice it's not coming to exactly the same conclusions. The p-value is 0.003. It's very close. You're not going to substantively draw things differently. But it's a different way, but it's not as, I don't think it's as robust as the -2 log likelihood difference. That's if you can do that, that's a cleaner way to test the difference. So we've got the regression equation, right? The log odds is equal to 4.6123 minus 0.4411 times parent schooling. We can convert those to probabilities back with that formula we looked at earlier. I mean, instead of just talking about, well, what's the odds ratio, we can actually say, well, what if a kid is in, a specific grade? Let's say someone is in 7th grade. What's the probability based on this model? What would I predict is the probability that they'll drop out, that there'll be a 1? Remember, that's what we're predicting, the probability there'll be a 1 or drop out. So you just take this funny looking formula, 1 divided by 1 plus e to the negative regression equation. You just plug in the regression equation, or you can solve the regression equation and plug in the value. Make sure you do negative, whatever that value is. So we do 1 over 1 plus e to the negative 4.6123 minus 0.44111 times 7 gives us 1 over 1 plus e to the negative 4.6 minus 3.08, or 1 over 1 plus e to the negative 1.52, or 1 over 1 plus 0.2177, or 0.8212. That's the probability, that's our predicted probability of dropping out if the parents had 7 years of schooling. We can do the exact same thing with a different value. What about if they had 12 years of schooling? And we just take the exact same equation, but now we plug in a 12. And you get blah, 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 down to 1 over 1 plus e to the negative 4.6 minus 5.29, or 1 over 1 plus e to the negative 0.68. Keep track of those double negatives, which is 1 over 1 plus 1 over 1 plus 1.979, 1 over 1 plus 1.9757, or 0.3361 is the probability with 12 years of schooling. It is a tough school, tough community. Okay? So you can do that, and you can see, if we start to run out of time, how you could plug in all sorts of different values and create a graph, a figure of those probabilities for different values to get a sense of kind of not just the odds ratio that tells you the effect of cumulated, when you're kind of increasing risk, but also kind of the overall probabilities across the whole range. Another way of evaluating a logistic regression is based on how well it accurately predicts